Okay, welcome back. In this video, we're going to talk about log functions. To start talking about log functions, we really should start with exponential functions. So I'm going to look at this expression, b to the x equals a. So this might be something like 2 to the x is equal to 16. But I'm going to leave it general. I'm going to define the following function. A function that allows me to rewrite this relationship between these three objects, the b, the x, and the a, to isolate for x, to get the x all by itself. This is like a translation. We're taking the same information, b to the x is equal to a, and we're translating it into a different language. So it contains the same information, but it's stating it in a different way. In this format, the x is all by itself. And we write it, x equals log base b of a. That is the definition of a log function. It is a way to manipulate an exponential expression to isolate for a different component of it. Something to keep in mind is because the exponential function always gives positive y values, we can't plug a negative number into a log function. It doesn't make sense. It's not possible, at least not with the number system that we're using. Another requirement is that the base of a log function must be positive, and that's mirroring the requirement that the basis of our exponential functions must be positive. The number, that little b that's appearing in the log, so that is a subscript b, it's called the base of the log function in the same way that in the above exponential, b is called the base of the exponential function. So they're both bases. So again, the definition of a log function is it's just a way to manipulate an exponential expression to isolate for a different part, to isolate for what's inside the exponent. So we take these two statements as equivalent. X equals log base b of a, it means the same thing as b to the x equals a. That relationship at the very start gives us our first log property. So based on this construction, like this is the starting point. Based on this, I can take x equals log base b of a and take that a that's here and use the fact that a equals b to the power of x and replace the a with b to the x, and I have x is equal to log base b of b to the x. This is our first property of logs. It's called the cancellation law. And there's actually two cancellation laws. This is the first order of the cancellation law. The other order is b to the power of log base b of x is equal to x. What's happening is this. When you take an exponential function b to the power of x, let's say 2 to the power of x, you're performing the exponentiation operation on the x value, whatever you plug in. You're raising some constant base to that power. The log operation is the opposite operation. Whatever that exponentiation operation is doing, log does the opposite of that. So if you put them together, if you take log base b of b to the power of x, so b does something, the base b on the exponential does something to x, log base b does the opposite to that, so you get the original. It's like nothing happened. You can think of it as maybe rotation. You rotate counterclockwise 90 degrees, and then you rotate clockwise 90 degrees, and end up in the same spot. They're opposite operations. Or you can also think of it as multiplication and division. Multiply by 2 and divide by 2. The answer is going to be the same after performing both of those operations back to back. So some examples of cancellation law, log base 5 of 5 to the x is equivalent to just x. Whatever you plug in for x, let's say you plug in a 2, log base 5 of 5 to the 2, so that's log base 5 of 25. Log base 5 of 25 does the opposite. It's just the opposite operation. So it's going to undo whatever was done to 5. Log base 9 of 9 to the 8 give you 8 back. There's other ways to describe what a log function is. There's some cute graphs. There's cute ideas linking it to multiplication and subtraction. Like there's different ways you can formulate an understanding of what a log function means. But I don't think anything is better than just accepting that a log function is a function defined with this cancellation law. This cancellation law just comes from accepting that x equals log base b of a means the same thing as b to the x is equal to a. And I'll talk about this, and I think very soon, in relationship to other inverse operations that you already know, other opposite operations that you're already familiar with, and hopefully that will help make sense of it. Let's just get into manipulations before we do that. So we'll accept at face value that we have this cancellation law and look for opportunities to use it. Log base 10 of 100. If we're asked to simplify this, chances are the simplification will come from using a cancellation law. In its current format, the cancellation law can't be used. We need log base 10 of 10 to the power of something in order to use a cancellation law. Can we write 100 as 10 to the power of something? And the answer is yes. We can write this as log base 10 of 10 to the power of 2, since 10 to the power of 2 is 100. Now the cancellation law allows us to cancel log base 10 and exponential base 10, and we're just left with whatever power is there, which is 2. Next one's the same idea, log base 2 of 8. Well, I can't do anything in its current format, but I can replace 8 with 2 to the power of 3. I'm choosing that replacement because it makes the base of the exponential function match the base of the log function, which allows the cancellation law to be used. And I don't know how much of this is review for everyone. Prior to taking a course in calculus, you're supposed to take a course in advanced functions or algebra 1, algebra 2, and that's supposed to contain logs, but I don't know what's done in all those different courses. Every high school in the world, even every high school in the same province or the same city is going to cover things a little bit differently. So anyways, I assume you've seen the cancellation law at some point. You may have written it out a different way, you may have had it explained a different way, but I assume you've seen it already. Okay, next one. In order to access the cancellation law, we need to write the interior, 1 over 27, as 3 to a power. And it can be done. We're going to do it in 2 steps. First step is 27 can be written as 3 cubed. Now it's not quite ready yet. The next thing I want to do is use that exponent rule for negative exponents. 3 to the power of 3 in the denominator can be rewritten as 3 to the power of negative 3. Now we have the bases of the log and exponential matching, so we can use the cancellation law. Notice we could not use it in the previous line, in the previous form, with the 1 over 3 to the 3 with a 3 in the denominator. We have to bring everything up in order to use the cancellation law. We get negative 3. And the last one, what do we do here? How do we use the cancellation law? Well, this is just recognizing that if there's no exponent on a number and you want there to be an exponent, you can always put a 1. 99 is the same thing as 99 to the power of 1. Oh man, I'm having some trouble writing a 1. So we can use the cancellation law and just get 1. Some people like to think about this translation idea a little bit more deeply. That exponentials and logs are like, let's say, French and English. You have one that you're more familiar with, exponential functions, one that you might be less familiar with. And the name of the game is when you're trying to let's say, wrestle with a complicated expression in a language that is not your first language, you try as much as possible to translate that expression back into your first language. So if you have an expression involving logs, a equals log base b of x, you can immediately translate it into x equals b to the a and work on it from there. So some concrete examples, 4 equals log base 2 of 16 looks kind of mysterious, looks kind of weird, But if we translate it into our native language or language of exponents, it says 16 is equal to 2 to the power of 4. If we take the expression 3 equals log base x of 27 and solve for x, well, it looks like maybe impossible. It looks completely bizarre. But if we rewrite it, if we translate it from log form to exponential form, 27 is equal to x cubed, which isn't hard. What number raised to the power of 3 gives you 27? The answer is 3. But in the first format, what on earth are we supposed to do? So I invite you to think about this. I don't know if it's wise to approach log problems by translating all of them into exponentials, at least not directly, with no step in between. I'll show you what type of step you can use so that you have like a sequence of operations. Anyways, but the idea is there, and some people really like this idea. That's just a translation from one language to another. Okay, so I promised I'd explain a little bit better about what log functions are and how they relate to exponentials. And this, I think, really captures the important ideas of this log exponential relationship. And it requires us to go back to simpler mathematical operations, like the difference between multiplication and division. The expression 5x equals 10 can be rewritten. We can isolate for x by performing an operation on both sides of the expression. The operation I'm going to perform on both sides is division. So x is equal to 2 using the opposite of multiplication by 5. Which is division by 5. So something's being done to x, and we want to undo that thing. We want to undo the multiplication by 5, so I'm going to divide by 5. And then in the next one, I have x divided by 5 is equal to 10. I want to get x all by itself, so I want to undo the division by 5. I want to do the opposite to division by 5. So I'm going to multiply by 5. I get x is equal to 50. Using the opposite of division by 5, which is multiply by 5. How about the next set? I'm actually going to add some language here that multiplication and division are inverse operations, that they do the opposite. One does the opposite of the other one. Next one, the third root of x is equal to 4. How do we rewrite that? Well, that means x is equal to 64, but how do we get that? So we're going to use the opposite of cube root. We're going to raise both sides, or not raise both sides. We're going to apply power 3 to both sides. On the left-hand side, we have the cube root of x, all to the power of 3, which is just x. The cube root and power 3 cancel. On the right-hand side, we have 4 to the power of 3, which is 4 multiplied by itself 3 times. So we're doing the opposite of the thing that's being done to x to get x all by itself. Next one, x to the power of 5 is equal to 32. Well, we want to do the opposite of what's being done to x. So that has to be done to both sides, and we get an answer. X is equal to 2. Using the opposite of x power 5, we're going to take the fifth root. So roots and powers are opposite operations. Now the last set would be the new set. This is the new thing. 5 to the x is equal to 32. I want to get x all by itself, so I have to do the opposite of raising x as a power on 5. This is not taking a root. Right? Taking a root isolates for the base, but I don't want to isolate for the base. I want to isolate for the power. And the operation that does this is that log operation. I'm going to get x equals log base 5 of 32. Which doesn't simplify. There's no nice number that comes out, just log base 5 of 32. So we're doing the opposite of exponentiation. We're logging. Take log of both sides. We're taking so the opposite of exponentiation with base 5 is take log base 5. Of both sides. And the last one, log base 5 of x is equal to 2. We have to do the opposite of taking a log base 5 both sides, and the opposite here is to exponentiate both sides. We get x equals 5 to the power of 2. That one simplifies, that one's 25. Using the opposite of log base 5. So this is exponentiate on base 5. So we're just defining a new operation as an opposite to the exponential operation, just like we have x to the power 5 matched up with fifth root of x. Multiplication by 5 matched up with division by 5. So it's just about combining these, not combining, just defining a partner, an opposite operation to partner with exponentials. So we saw that we can take log base 2, we can take log base 5, there's different log bases. We tend to stick to a small number of log bases. We tend to stick to log base 10 because our number system is base 10. Our number system is base 10 because we have 10 fingers. So it's very, very much related to our to human anatomy. This common logarithm, log base 10. And the log base that we use is not related at all to our anatomy, not related at all to our financial system or our number system. It's log base e. It's so-called natural log because it has nothing to do with us. It's just the log base that the universe likes the most. This log function, log base e, is called ln, ln of x. It's not written out normally as log base e because that's 4 characters and it comes up so often that we just shorten it to ln of x. No matter what type of log base we have the same laws of logs. I'll go through them. For m and n being positive numbers, and b, the base of the log function being positive and not being equal to 1, we have the following properties. First log property is log base b of m multiplied by n can be rewritten as log of the first plus log of the second. Now the base doesn't change when we do this. The base stays the same in all three pieces. If we are instead dividing m and n inside the log, then that turns into subtraction. If we have the log of something to a power, it is a law of logs that we're allowed to bring the power down in front. So log base b of m to the power of n is equal to n times log base b of m. So wherever that power is, the power comes down. This is independent of derivatives. It has nothing to do with calculus. It's just a function property of logs. The next thing's more of a definition, not really a law. Log base b of 1 is equal to 0. I'll explain why in a moment. Next thing's similar, it's just a property. Log base b of b is equal to 1. Looks mysterious, but I'll explain why that's true. The last one here is the log conversion formula. If you have a log of a base that you don't like, let's say a log base 7, and you want to know what log base 7 of that number is, let's say, what is log base 7 of 10? You look at your calculator, you don't have a log base 10 button or log base 7 button on it, but you do have a log base 10, you have a log base e. Well, what you do is you convert it to one of those bases that you have using this formula. So log base 7 of 10, you'd rewrite as, let's say, log base e of 10 divided by log base e of 7. Then you'd be able to compute that on your calculator. So that's primarily how this formula is used. Here's a special case with log base e being rewritten with ln. Special case of this law. Now, where all these come from is they come from the laws of exponents. The first rule is that the translation into log language of x to the m times x to the n is x to the m plus n. The second one, you might be able to guess, is the translation of x to the m divided by x to the n is equal to x to the m minus n. If we translate that law from exponential language into log language, we get this law. The next rule is a translation of this law. X to the m to the n is x to the m times n. Okay, the next one, if we rewrite this in the language of exponential functions, so use that translation idea, then it says that 1, the number that's inside the log, is equal to the base, b, to the power of the thing that was all by itself. So b to the power of 0 is equal to 1. Just translating that expression from exponents, anything to the power of 0 is equal to 1, translating to logs, it says log of 1 is equal to 0 for any base. The next one is equally ridiculous looking after we translate it. It says that b is equal to b to the power of 1 translation. And then rule 6 is a combination of exponent laws. So in truth, there's nothing new compared to the laws of exponents. The laws of logs are just those exponent laws translated into this log language. They do look weird though. So I'm going to do a little bit of practice of manipulating the expressions using log properties. This is mirroring the types of operations we're going to do later on in larger problems. So here it's isolated, just do this one thing. But in a larger question, there might be 6 or 7 steps, and the step we're about to do would be one of those steps. So we're just focusing on that part. So the instructions in the first question are to combine these into one term. And the log property I'm going to use is the log of m plus the log of n is equal to the log of m times n. So we're going to say that this is equal to the ln. All my L's are curly when I write ln, and when I write log, they're not curly. I don't know why, and I can't stop. Can't stop myself from curling the L on the ln. Okay, so that's our property, log of m times n. And we can FOIL, collect like terms, simplify it, we get x squared minus 25. Okay, the next one, combine into one term. Here we have to use two rules. We have to use the ln of mn rule, or I should say log rule, and the log of m over n rule. We need to use both of those rules. So I'll do the first two. We have the ln of the first divided by the second, 4x minus 18 over 2x plus 6. We have plus the ln of x. So what we did there was we did the ln of m divided by n rule to combine those first two terms. Ln of m minus ln of n is ln of m divided by n. Now we have to combine these two together. So now that bracket, that giant bracket, the first piece, that whole thing is m, and n is just the x in the second term. So the ln of 4x minus 18 times x over 2x plus 6. And we can simplify. This is the ln of 4x squared minus 18x all over 2x plus 6. You can factor out a 2 from the top and bottom if you want and cancel it, but you don't have to. Okay, the next one is tricky because we again have to use two rules, but we have to use those two rules in a particular very careful order, very careful way. This log property, ln of m plus ln of n is the ln of m times n. Notice that we can only use it if the constant in front of the log is 1. If there's some other constant in front, we cannot combine the terms. So what we have to do first is we have to get rid of those constants in front. The 2 that's in front of the first term and the 3 that's in front of the second term. We can't combine these into one term until those constants are gone. But how are we supposed to get rid of them? Well, we're going to use the log of m to the power of n is the n times the log of m. Bring the power down, except we're going to use it in reverse. We're going to bring the power up. It's already down. We're going to do it backwards. So the ln of x plus 1 all squared plus the ln of x all cubed. And now we can use the rule to combine the pieces. We have the log of m log of m plus the log of n is the log of m times n. So we have the ln of x plus 1 all squared times x cubed. And that's been combined into one term. You can FOIL it out if you want, expand, or leave it alone. It's up to you. Next, combine into one term. We're going to do the same thing. We're going to bring those powers up on top. We don't want those numbers up on top as powers. When we want to combine log pieces, we don't want coefficients in front. We want to move the coefficients up as powers in order to do the combining. So we're going to do log of m to the n is n times log of m. I'm just going to go backwards. We're going to bring the numbers up as powers. We have the ln of x squared plus 4x to the 1/2 minus the ln of x minus 1 squared. So a natural question to ask is, could I also brought up the negative sign and change it to a plus in between? Absolutely. It'll give you the same answer. I'm going to leave it as a minus. I'm also going to do another step before combining these pieces. I'm going to rewrite this as a square root. Power 1/2 means square root. And the next step, and that square root conversion had nothing to do with logs, it was just an exponent law. And then the last step is I'm going to combine the log pieces, log of m minus log of n. There's the log of m divided by n. So I'll rewrite this as the ln of the square root term divided by x minus 1 all squared. Now it's been combined into one term. Some things you cannot do with logs. Things that you'd be tempted to do. So starting with things that you can do. If you have a log of a top expression over a bottom expression, it's perfectly valid to split it up as the log of the top minus the log of the bottom. That's fine, that's allowed. But you cannot split it up as the log of the top divided by the log of the bottom. You can't distribute the log to the top and bottom separately. It just doesn't work. It's not true. Likewise, if you have the log of two things added together, you leave it alone. The log of a plus b is just the log of a plus b. You cannot split it up as the log applied to each term separately. So I put these two as examples of the types of ways that students are often tempted to abuse log properties. The red X's just indicate you cannot do that. It's never allowed. It's never valid. Now, in addition to being a function that's defined through this inverse property with exponentials, log is a true function. And like all true functions, it has a graph. So I've graphed the function 10 to the power of x in red. On the same graph, I've graphed log base 10 of x in blue. One nice feature of inverse functions is that they are reflections of each other about the line y equals x. So if you graph square root, or let's go cube root of x and x to the power of 3. I'll do that on Desmos. We'll get Desmos back here. X power 3, x power 1/3. I gotta change my axes. Let's go minus 10 to 10. Okay, so there's the two functions. I'm also going to graph the line y equals x together. And the green curve and the purple curve are reflections about that black line. I can do 3 to the x and log base 3 of x are also reflections about that line. That's always going to be true of the pair of a function with its inverse function. That's actually one way to create the graph of the log function, is to graph the corresponding exponential function that has the same base, and then do a reflection about the line y equals x in the same way that you would do a reflection of a picture in art class. Here's three different log functions graphed together. Notice that the larger the base of the log function, the more slowly it grows. Log base 4 of x grows more slowly than log base 2 of x. The graph of ln of x, log base e, doesn't look special, right? It has the same shape as log base 4 and log base 2. E, 2.7, is between 2 and 4, and it makes sense that the graph of log base e is between the graph of log base 2 and the graph of log base 4. So that part's reliable and normal. Talked about those properties, I guess, except continuity. The log function, like the exponential function, is continuous. It doesn't have any holes, doesn't have any vertical asymptotes in its domain, in between 0 and infinity. It doesn't have any jump discontinuities. It's a nice, smooth graph. I mentioned the cancellation law already, but I want to write them down in kind of formula format so they're clearly indicated somewhere in the notes. The cancellation laws are as follows. Here's both of them. A to the power of log base a of x is equal to x, and log base a of a to the x is equal to x. So an exponential function and a log function that have the same base, if you put them together back to back as composite functions, they cancel each other. And you get the original argument out of each, independent of which order that you do them in. Even though these are the same cancellation laws, I'll rewrite them for log base e anyway. So you have it in the notes somewhere that e to the ln of x is equal to x. Remember, ln means log base e, so this is just the same cancellation law as this one. Replace the a with an e, just replace one arbitrary letter of our arbitrary alphabet with another arbitrary letter of our arbitrary alphabet. And ln of e to the x is equal to x, because ln means log base e. Okay, so I'll solve through some of these. First one, and I think most of them are asking us to solve for x. The first one's asking us to solve for x if log base 3 of x is equal to 5. And our solution, the best way to get the solution, yes, you can do it by translating, but the best way is to exponentiate. Raise both sides as powers on the same base. We're doing that because that operation, exponentiation, is the opposite of the log operation. And the log operation right now is what's trapping the x. We want to untrap it by doing the opposite operation. I'm using base 3 to match the base of the log. So 3 to the power of log base 3 of x equals 3 to the power of 5. I have a cancellation law, and x is just 3 to the power of 5. Next one's the same. This time the log function has a base of 5, so I'm going to exponentiate both sides as powers on a base 5. Log 5 to log base 5 of x is equal to 5 to the power of 2. We can cancel, and we get x is equal to 5 squared, which is 25. Notice I didn't simplify 3 to the 5, but I did simplify 5 to the 2. That's just whether or not I know it. I don't know what 3 to the 5 is. I'd have to do 3 to the 4, 81, and multiply that manually by 3. And I don't want to. 243. Okay, next one. Ln of x is equal to 3. Ln, remember, means log base e. So to cancel, I'm going to exponentiate. I'm going to raise both sides as powers on the same base. I'm going to use a base of e. E to ln of x equals e to the 3. And then cancel. And that's all we can do. We can say x is equal to e3, e power 3. It's a weird unending decimal number. That's okay. Okay, now these ones are different. These ones we can't start by exponentiating. We have log functions. We want to get rid of the logs. But our first step is to isolate for the log function. And there's two different ways we can do it. One way is we could bring the 4 up as a power. That's fine, that's valid. The other way is to divide both sides by 4. It's also valid. I think it's easier to divide both sides by 4, so that's what I'm going to do. So ln of 5x plus 2 is equal to 8 divided by 4, which is 2. Now I'm going to raise both sides as powers on the same base. I'm going to use base e because that'll cancel the ln. So e to the ln of 5x plus 2 is equal to e to the 2. I'm going to cancel. So 5x plus 2 is equal to e squared. 5x is equal to e squared minus 2. And then divide both sides by 5. X is e squared minus 2, all divided by 5. So we have to do a few operations there to get the x all by itself, not just the opposite of the log. You have to do the opposite of the adding and the opposite of the multiplying as well. Okay, then one in the middle, we can go directly to exponentiation because there's no constant in front of the log. There's no manipulation being done to the log function. It's just a log of something. So I'm going to exponentiate, raise both sides as powers on 2. So 2 to the power of log base 2 of 3x plus 5 is equal to 2 to the power of 3. I can cancel the 2 power log base 2, and I'm left with 3x plus 5 is equal to 2 to the power of 3, which is 8. 2 times 2 times 2. Now I'm going to subtract 5 from both sides. So 3x is equal to 8 minus 5, which is 3. Then divide both sides by 3, so x is equal to 1. Okay, now right hand side, the log is already all by itself. We don't need to manipulate. We can go directly to exponentiation. So 4 to the power of log base 4 of 5 minus x is equal to 4 to the 2. We can cancel. So 5 minus x is equal to 16. I'm going to subtract 5 from both sides, so negative x is equal to 11. And then divide both sides by negative 1. So x is negative 11. Okay, I'm not going to do the bottom left right away. I'm going to do the bottom right first, since this is the same format, solving for x. I have 5 equals log base 2 of e to the x plus 5. So right now the x is trapped in an exponential function, and it's trapped in, from there, it's trapped in a log function. I have to work from the outside first. So I want to deal with the log function first, because it's the outermost operation. I'm going to get rid of it by exponentiating, raising both sides as powers on a base of 2. So 2 to the power 5 is equal to 2 to the power of log base 2 of e to the x plus 5. I can cancel on the right, 2 power log base 2, and we're left with 2 to the 5, which is 32, is equal to e to the x plus 5. Okay, now we have to get the e to the x all by itself. So I'm going to do the opposite of add 5. I'm going to subtract 5 from both sides. So 32 minus 5, 27 is equal to e to the x. Now I'm going to take the ln of both sides. Ln of 27 equals the ln of e to the x. Ln means log base e, so I can do a cancellation there. And we have x left over on the right equals the ln of 27. That's our answer. Now bottom left. Simplify. So it's not solving for x, it's just simplifying using the laws of logs and laws of exponents and the combination, the cancellation law. So log base 9 of 81. I can write 81 as 9 squared. I'm doing that to get access to the cancellation law. E ln 3 I can just immediately cancel into a 3, since the bases already match. 9 log base 9 cancels, and we get 2 minus 3, which is negative 1. So these are somewhat straightforward, simple examples. They're kind of mechanical. The mechanical process is if the log function is all by itself right away, then you exponentiate to use a cancellation law, and you match the bases so that cancellation law is accessible. If the log function is not all by itself, then get it all by itself. Add, subtract, multiply, and divide so that its log of stuff is equal to other stuff, and then exponentiate. I'll continue with the next video. It's almost 45 minutes. I'll continue with the next topics, next examples in the next video.